So, okay, let us now go to the third problem. This is the third question. So, this is a problem of the 3D geometry. Okay. So, they have given two lines in a 3D plane, line 1 and line 2. So, they have given the coordinates and a parameter lambda. So, we need to find the lambda first. Okay. So, they have asked for that given point 2, 3 and 4, this point is the closest to line L1. So this is the line, this is the coordinate that is closest to the line L2, this L1 and L2. So this point is closest to the line L2. So what will be the corresponding point on L2? So they have asked for what is the corresponding point on this line L2. So we'll be dealing with this. So they have given coordinates, means the parametric form of these two lines we can see, and the point on L1 that is closest to the line L2. Okay, so for this we need to find the parameter lambda. Okay, so we need to find the parameter lambda for the closest point. That lambda we need to find out, and then find the point on L2. In this thing we'll need one concept, that is the vector. We know that we know this theory that vector connecting the closest point, the vector that is connecting the closest point on two lines is orthogonal to the direction vectors of the both the lines. So the vector that is connecting the closest point on two lines is the orthogonal to the direction vectors on both the lines. So we need to find the direction vector of these two lines. So the direction vector, we can see the coefficient of lambda in line L1. So from this I can plot the direction vector, that is d1. Okay, let us say d1. So the direction vector will be 1, 2 and 3, the coefficient of lambda. So the coefficient of lambda in L2, that is 1, because there is no lambda in this y, so it will be 0 and it will be 1. So these are the directional vector. Okay, so a general point is given in L2. A general point is given, that is 4 plus lambda. Okay, 4 comma and z is 4 plus lambda. Okay, z is also 4 plus lambda, isn't it? Yeah, z is also 4 plus lambda. Okay, now the vector connecting to this, the vector connecting from that L1 point, that is 2, 3 and 4, the vector connecting from this to this point are these two vector is equal. So means the positional vector of that means, if I calculate the vector, the connecting vector, so this is this minus this minus this minus this. So the vector will be subtraction of these things. So 4 plus lambda minus 2, then 4 minus 3 and 4 plus lambda minus 4. So what is the connecting vector? The connecting vector is 2 plus lambda, 1 and lambda itself. So this is the connecting vector. Now since this vector is orthogonal, so this vector is orthogonal to d2. So this vector is orthogonal to d2, this direction. So that according to the property, so the dot product of these two things will be 0. We know that the orthogonal and the direction vector dot product will be 0. So we will use this concept. So now if I do the dot product of this, which one? The dot product of 2 plus lambda 1 lambda dot 1 0 1. So we'll be getting 2 plus lambda 1 plus 1 into 0 plus lambda into 1. So if I solve this, I'll be getting lambda equals to -1. So this is the parameter. Okay, so this is the parameter. Now the job is done. We have got the parameter. Now just substitute in the L2 parametric form. So if I put that in L2, that is 4 plus lambda that is given, so -1. Okay, the next one is 4 and the next one is 4 plus -1. So the point on L2 is 3 comma 4 comma 3. So this is the closest point. So this is the point on L2 corresponding to the point that is on L1, that is 2, 3 and 4. So this point will be touching L2 at the point 3, 4 and 3. Okay, so this is the shortest closest to L2. So this is the answer. So the option will be A, I guess. Yes, A.